Good morning, good afternoon, and good evening to everyone joining us from around the world. My name is Wei He, and I am the commercial manager of Neuroscan Compumatics. So on behalf of our entire team of Compumatics, I'd like to extend our very warm welcome to this session of the NeuroTalks. Compumatics is proud to host this series as part of our commitment to advancing neurological discoveries and clinical care through innovative technology. Today, we are thrilled to continue that conversation by exploring the EEG and MEG source imaging with the maximal entropy on the MEM framework. Our distinguished speaker for this session is Dr. Christophe Grova. Dr. Grova is a professor at the physics department at Concordia University and a research member of Concordia School of Health since July 2014. While remaining adjunct professor, attended at the Biomedical Engineering Department and the Neurology and Neurosurgery Department at the McGill University. He is also affiliated to the epilepsy group of the Montreal Neurology Institute, MNI, the Cornell Brain Image Center of the MNI. Before I hand it over, a quick housekeeping note. We will have a Q&A session after the presentation. My colleague, Dr. William Oliver, will actually lead that session. So if you have questions, please submit your sessions using the question feature at any time on your right side of your, I think it's on your right side of the screen, at least that's what I see. There is on the top, you see there is a question mark. Click on that, and that's where you type a question and submit the questions. So, this session is also being recorded and will be made available later. So before started, I like to do a kind of a fulfill of the compliance. So let me actually read a disclaimer here, as we always do, to meet our compliance requirements. All right. So the information in the NeuroTalk webinar represents the view and opinions of the presenter and does not necessarily represent those of the Compumatics. Compumatics does not make any representations or warranties regarding the accuracy, applicability, fitness, and completeness of the information presenters during the talk. The information presented in the webinar is not intended to be a substitute for professional medical advice, diagnosis, or treatment. Compumatics does not seek product promotion, sales generation, or any other commercial value through this webinar. All right, so let me stop the sharing, and I will make Dr. Grova, will be the presenter. So hold on. Yes. All right. So without further ado, it is my great pleasure to introduce Dr. Grova.
Okay. Can you see my slides?
Yes.
Yes. Okay. Perfect. So I'm gonna start. I'd like to first thanks a lot you, Wei, and Tara for the nice invitation and for giving me the opportunity to contribute to this very interesting series of talk. So what I'm gonna present today is we'll do a tour of some tools we have been working on since many years now, which are called MEM for maximum entropy on the mean, and that we mainly apply to either EEG or MEG source imaging, mainly in the context of epilepsy. So I'm going to go over that, and I will mention also that those tools are available. We implemented them mainly in Brainstorm software. So this is our topic. I will first try to explain you why it is of interest to localize a generator together with its spatial extent. And that is, I think it is feasible with our technique. And then we'll move to source imaging of oscillatory patterns, so notably ictal patterns, but also resting state oscillations and functional connectivity. At the end of the talk, I will show you some interesting, promising results we have with the team of Christian Bénard in Marseille, where we are actually validating our method using MEG and intracranial EEG stereo electroencephalography simultaneously recorded. So first, as most of you know, and this is a very famous slide from the group of Tao, when you record a spike, an epileptic spike on the scalp EEG, it would look like that, and it's going to involve few channels. But when, and these were data that were simultaneously recording with intracranial EEG, and at the same time, you see that, of course, lots more is going on. And there have been different studies that shows, including the one from Tao, that we need relatively extended regions of cortex to be active to see those discharge, which are large signal to noise ratio signal on the ongoing scalp data. And typical results are suggesting that we need, I would say, at least 4 to 8 square centimeter to see the spike on EEG, perhaps slightly less in MEG, but still it's extended. And those results might not be that accurate, especially because they've been compared with ECOG, with grid, not with SEEG. So we're not covering the exact extent of the cortex. And also when you place an ECOG grid, you might have attenuation and amplification of the signal, as my colleague Nicolas van Ellenrieder showed in this very interesting paper. So I'm going to go through this method that I co-developed with my collaborator Jean-Marc Lina here in Montreal, called maximum entropy on the mean. And today we're going to review two main flavors, I would say. First, MEM in the time domain, which is typically designed for nice brain response, so epileptic spike, ERP, and to measure the generator together with the spatial extent. And then we're going to use the wavelet extension to do this localization in the time frequency domain to localize oscillations. So I'm going to start on this. So this is my only a bit technical slide. I can provide even more mathematical framework. You have some papers here. Just explaining very briefly what is MEM. MEM is a Bayesian technique. It's like other typical Bayesian method like S-Loretta, Loretta, minimum norm. So you start with a prior definition, which is a reference distribution. We have an infinite number of possible distributions that explain the data. And here we're going to use, if we find a solution that explains the data, I'm going to use information theory. So I'm going to measure relative entropy to measure the kind of distance between those two. And I'm going to choose the one that is the closest. So as in maximum likelihood, I want a balance between a solution that explains the data and it's close to my prior. So I won't say more than that. The only thing that I think is interesting in MEM is the fact that our prior is a parcellation of the brain. So we consider the brain to be organized in K parcels, and those parcels might be active or not. So if you want, the method is able to switch off parcel, and when the parcel is on, we have a Gaussian prior, which is a kind of Loretta prior. So minimum norm plus some local smoothness, if you want. So this is it. I will also mention that the number of parcels is usually roughly the number of channel of our data, so around 100, 200. But it's not a tricky part. Whatever is the parcellation, the solution will be quite stable. It's a regularization technique. So just to show you first that it is indeed sensitive to the spatial extent, this is the first study that we did on simulation, on noise-free simulations. We simulated an extended sources and we look at the spatial properties of MEM compared to different techniques like MNE, S-Loretta, DSPM. Of course, all the methods localize the maximum very well, but we have more spatial spread in those linear techniques, either in MEG or high density EEG. And this is for localization of the first peak of an electrical medial nerve simulation. Same, the peak is well localized, but the spread, it's a little bit more focal or locally focal in MEM. So more importantly, I will go to epilepsy now, and I'll show you different way we tried to validate. The first thing we did with Dr. Pellegrino was to compare MEM localization with what is approved in clinic, which is standard dipole localization. We did that in 49 patients. So the ground truth was given by the clinical knowledge or presence of surgery when it was available or EEG. And what we found out is that, first of all, dipole modeling was quite nice because it was very good and concordant with the presumed focus. It's 70% of the case, but with MEM, we were improving by 10%. So we were more stable. And then we did the same study on similar patients, but this time on distributed source imaging. So here you have a patient who has actually a focal cortical dysplasia here, and you have the spike localization, MEG spike localization using MEM, S-Loretta, MNE, and DSPM. So these are non-thresholded map on purpose, just to show you how sensitive we are to that spatial extent. And if we threshold a little bit, we're going to get that extent. So there is no, it's quite robust to that. And actually, as you can see here, all the methods were localizing the presumed focus very well in terms of distance, but in terms of spatial spread around the focus, MEM was way better than the others. And that's what you can see here on 12 subjects, where you see the different maps that are non-thresholded and thresholded. So you see how focal and how relatively clean are those maps. We then try to further investigate that with this study. So in this study, done in collaboration with Birgit Pauscher and John Gutman, what we did is we acquired EEG and MEG first, and then we acquired simultaneous EEG and fMRI. So I will not go in the detail of that technique where Dr. Gutman is a pioneer, but basically you detect the spike on your EEG in the MRI scanner and you look at the hemodynamic response to that. So the blood flow response to the spike. And then we had intracranial EEG. So of course, non-simultaneous, but then we tried to compare all that. And I will show one method that I developed a few years ago because I'm going to use it in many studies today, is we record MEG, we reconstruct MEG along the cortical surface, but then we want to see what's the link with intracranial EEG. So what we decided to do is to transform our MEG sources into intracranial EEG data, because SEEG is our gold standard here. So we want to see what portion of the MEG can be seen by intracranial. And to do that, we apply an intracranial EEG forward problem to this. So we have measurements of magnetic field in picotesla, transform into source map, and then transform into electrical potential as what I would call virtual SEEG potential, estimated from the MEG. And this is just to give you an example on one spike. This is what we actually record on the patient, and this is what we could reconstruct on a series of electrodes. So in this study with Dr. Abdallah, we did this. So here you have one patient example. You have EEG and MEG spike with a localization down here. Then we selected the spike in a SEEG, and you see the average spike here, plus the selection of a seizure. And we identified the first point where the spike was rising, the peak, and the beginning of the seizure as well. And then we projected those MEG map into the SEEG space by doing this projection that I just explained. So this is the average SEEG signal, and this is the SEEG signal that has been estimated from EEG MEG sources. And you can see how similar they are. And then we could compare, because from the SEEG, we can define this is the irritative zone where the spike are localized. This is the seizure onset zone where seizures are localized. And then we could project our map here and compare. And we did the same projection for fMRI. So in that study, I will not go in all the details, but basically we did measurement of spatial overlap. So we had subjects that were showing good or poor spatial overlap when we were comparing the spatial overlap of the spike map from EEG MEG or fMRI with our SEEG ground truth. And what we found out is EEG, MEG localized actually very well as expected, the primary irritative zone defined clinically on EEG. And interestingly, even if we were localizing spikes, fMRI was more localizing the seizure intent zone because fMRI is measuring hemodynamics or more metabolic aspect of that. So I will not say more about that. So this is to recover the spatial accuracy and the spatial extent. It was working well. And then let's go for oscillations. So just a bit of a technical aspect. If you have a signal here, you can decompose this signal into the time frequency domain. So you can have time here versus frequency. Here, this is not a nice continuous space. These are little boxes because we are using a tool that is called discrete wavelet. And through those discrete wavelet, what we can actually do is really to decompose very nicely the signal with nice properties. So for every channel, I can have one time frequency box on all my channel, and I can apply MEM to reconstruct the time frequency box in the source space. And I can do localization of specific oscillations. And I'll show you a few other examples. So in the first part, I show you that with standard MEM, we localize the spike quite accurately with their spatial extent. Now I'm going to show you that we can localize oscillations. So ictal oscillation, this is an old paper that we did in 2016 with Giovanni Pellegrino. So you have an example of a seizure here recorded in MEG and EEG. We identify the beginning of the seizure. We first look at the standard time frequency domain to find out the main frequency that were present there. And then we went to this discrete space. So these are these discrete wavelets to identify what time frequency box were the most important. And it looked like this box here between 18 to 35 Hertz correspond nicely to the very beginning of the seizure. And then for every box here, I can reconstruct a map. And then I'm going to select the box that were involved in that frequency at the very beginning of the seizure. And I can map the seizure onset zone like that. So this is a technique that is implemented in Brainstorm. And here you have an example. We have different small electrographical seizures that you can see in EEG here. And this is, there was a dysplasia here. You have the spike localization. And here you have all the seizure localization that were quite concordant. On the same topic, but this time in EEG, with my colleague Birgit Frauscher and with my previous PhD student Tamira Victor, what we did is we looked at spike and fast oscillation or gamma oscillations around the spike. So we look at those spikes to localize them using MEM, and we localize those gamma oscillations that were clear oscillations, not artifacts, using this wavelet MEM. And again, we see very nice correspondence between the fast oscillation localization and the spike localization for this small series of patients. I will now go to the second part of the talk, which is what can we do when, of course, we have a nice tool when we have epileptic discharge. So the main one are the spikes. And of course, when we have some chance, we can record seizures, or we have fast oscillation, HFO, but sometimes we don't have all of that, but we can still look at resting state activity. And there is a lot of literature on resting state oscillatory pattern or functional connectivity. And in this study, I will not do much epilepsy, but I'll show you the work we have done to validate, to show that our method is providing promising results where we hope we could use that as a clinical tool. So this is the work done by my previous PhD student, Jawata Afnan. So we want to do MEG source imaging of resting state oscillatory pattern in SEEG, in healthy subjects, and we want to validate at the population level with an atlas or intracranial EEG. And we're going to use this wavelet-based MEM. So to do that, we use this great atlas developed a few years ago now by Birgit Frauscher and Dr. Jean Gottman, which is a multicentric study that put together intracranial SEEG data from different patients, from different centers, but considering only healthy regions, so non-epilepsy regions using eyes closed, wakefulness, and this is the coverage they got at the population. They have even a better coverage now because this atlas has been extended. And this is a unique opportunity to have the spectral characteristic of non-epileptic, so I would say normal brain oscillatory activity at the population level in the brain. So what we did with Jawata is we selected 60 seconds of eyes closed resting state from this ground truth SEEG atlas, so 2,300 channels from 100 patients. And then we selected 45 healthy subjects on which we recorded 60 seconds of resting state. And this, we applied WMEM to do a source map, and then we transform using this method of applying an SEEG forward problem, we transform our source map into virtual intracranial EEG signals, and then we could compare those in different regions, and we also removed the aperiodic component. So this is just to give you an idea of our results when we compare the virtual intracranial space. So when we project in this SEEG space region by region and along the cortical surface for our method versus minimum norm. And this is different methods, so MEM, minimum norm, and beamformer in the different bands during resting state compared to our ground truth, which is coming from this atlas. And we retrieve the main patterns, being that theta is mainly frontal, alpha is more occipital, beta is central, and so on. So quite a nice representation. And just to go a little bit more in detail, here you have the lateral angular gyrus, and you see in black the population level of the intracranial EEG atlas, and in blue what we recover from MEG. This is before and this is after removing the aperiodic component. And you see in that context, there is a little shift here, but we retrieve the power spectrum quite well. And in this other example, now with the hippocampus, what we see is we are doing much more mistakes when we are localizing resting state activity in the hippocampus. And notably, we found a huge peak here in the alpha band. And this is probably due to some leakage because in SEEG, in intracranial EEG data, there is no alpha peak in the hippocampus. So I think we are good on cortical regions, but be careful on deep regions. This is a result that is summarizing that. So the color code means that the more red it is, the more concordant it is between what we reconstruct in MEM and what we measure from the intracranial EEG atlas. And when we remove the 1/f, the aperiodic component, the concordance is quite well. So we retrieve accurate MEG resting state oscillation in most regions in different frequency bands. Results were more comparable after removing the aperiodic component. Localizing deep structure remains a bit of caution, and especially might be biased by some leakage. Notably, we see an alpha peak in hippocampus, but not with intracranial EEG. And our method was good, but overall was not that different than minimum norm and beamformer for these large ongoing resting state oscillations. Just to let you know very quickly, here this is some work done by Winnie Vey in Duke with Birgit Frauscher, and we are reproducing this time on high-density EEG data, so 90 electrodes recording during the whole night, and with the new version of the atlas that is now considering sleep as well. So we were able to do the exact same comparison between localizing EEG in different sleep stage and converting to SEEG data and comparing to the SEEG atlas using the same technique. And you see some correspondence during awake between intracranial EEG and virtual estimated from high density EEG sources, but also during REM sleep in N2 and N3. I'll stop from there. So I'll now go to another part, which is quite used in the literature right now, is when we do ongoing resting state, we often like to look at link between regions and notably functional connectivity patterns. So we use with Jawata the same framework. So our comparison between MEG, healthy subject, and the intracranial EEG atlas as ground truth to compare to compare connectomes, to compare connectivity. And of course, because the atlas is compiling data from different subjects, we could not have a complete all-brain connectome. We could only use data when we had at least 2 channels from the same subject to be compared. So our ground truth here was actually 1,700 channel. So we have different numbers of almost like 20,000 possible pairs that could be generated. And for each of our participants, so for each of our healthy MEG subject, 45 subject, we record the whole brain ongoing resting state, and we could compute connectivity patterns on those exact same points, those 1,712 points, but we can do that for every subject for 45. And then we compare different metrics. So what are the main metrics? Usually to compare the link between 2 regions, either we can be based on amplitude, notably we can filter in a specific frequency band and we can correlate the amplitude. This is amplitude envelope correlation, or we can look at how the phase, like the phase locking value. So we compare those 2, and you might have heard about the problem of leakage in functional connectivity, is that everything that is time locked, that has no delay, might be biased by the inverse problem per se. So we are using some orthogonalized or specific version like weighted PLI, which are removing the zero-lag connectivity to not to be biased by the leakage. And so this is our framework. So let's say we have between 2 regions, let's say between the left cuneus and the left middle cingulate, we have 4 possible pair of channels coming from different subjects, and then from these pairs we have those, and so on. So because we have access to everything from our healthy controls after projecting in the EEG space, we are reproducing the same framework several times from our MEG data. And then from those pairs, I can do a connectome from the real intracranial EEG data, and I can do a connectome from MEG data converted into those exact same intracranial EEG electron. And then I was able to do a spatial correlation between those 2 connectomes. And because we have 5,000 value, I was able to do that 5,000. And then we were also shuffling the different anatomical label to get a null hypothesis version. So for instance, if I look at the correlation profile in the beta band, so here we have a minimum number of subjects in each regions. We are using around 30-ish region. So we have 5 subjects, and total the number of pairs that were considered here were 91, the minimum. And so here what we see is that this is the distribution of the null hypothesis, and the envelope correlations was doing a very nice, relatively high spatial correlation between what we measure in the atlas and what we recover from MEG converted in the atlas. And when we remove the zero lag connectivity that is biased, of course the connectivity decreased, but it's still valid. And we did that in the different band, and these are the results where you see that indeed the amplitude envelope correlated was quite nicely, and you reduce as expected when you remove the zero lag, but what remains is probably some of the true connections. And here you see our result for amplitude and also for phase measurements. And you see for superficial regions in blue and for deep regions in red. So of course, it's more interesting when you have methods that are sensitive to zero lag, they are a bit biased by high value. And when you are removing the zero lag, it's still a largely accurate, notably in alpha and beta band for envelope correlations, but be careful, especially for deep regions, the weighted phase lag index was quite inaccurate. So that was our main finding here. And if I may, I will just take 5 minutes to just talk about our very last and very promising results comparing MEG to EEG. So here was just, so far we showed that the intracranial EEG atlas is a good environment to do this validation for MEG resting state data. MEG resting state analysis is feasible and accurate, mainly in cortical regions. Let's be careful when we involve deep regions. And it remains quite stable, notably in the alpha and beta band. So removing zero lag seems important to remove the impact of volume conduction bias, but it could also remove some true connections. So last point, validation. This time, so far we were able to do a validation at a population level. So MEG healthy subject converting to the SEG Atlas space and SEG Atlas, which is a collection of multicentric data. And of course, EEG MEG is a non-invasive, it's ill-posed, it's difficult to localize deep structure or resting state and connectivity, and our ground truths remain SEG. So we are lucky that several teams, including our colleague, are started to consider simultaneous recording of MEG and intracranial EEG data. And here we want to validate spike localization, resting state power, so oscillatory power, and also functional connectivity power using the same metric I was showing you. So we initiate this nice collaboration with the team of Christian Bénard and Jean-Michel Badier in Marseille, and Jawata did all this work with Maria Fratello. And here, a few years ago, they published some seminal studies of their ability to record a patient with intracranial EEG data directly inside the MEG. Here we selected 9 patients. So we selected some spike, but we also selected some ongoing resting state activity, and we reported what was the main band during those. So this is our pipeline. So we collected MEG data, and we selected 1 minute of resting state clean data without spike and some spike. And then from the SEEG data that was recorded at the same time, we have the location of the electrodes. We also have 1 minute of resting state data, and we have the spike. And then for the spike, we applied MEM to localize the spike with the spatial extent using MEM, and then WMEM to localize ongoing oscillations and connectivity pattern during this 1 minute. And then we apply a SEEG forward model to have MEG estimated SEG, as I showed you before. So this is what we reconstruct from MEG in this SEG space, and this is what we measure directly, so we can do the comparison between those. And I'm almost done. So this is, for instance, an average spike, something quite standard you might see in MEG. And if you localize that spike, you're going to get a localization like that. At the same time, if you look at the SEG, this is where the maximum was found in this SEG. This is at the peak of the spike. And then when we converted those MEG data into virtual SEG, this is what we found. So it's not perfectly correct, but it's nicely concordant. And the distance between the max was 7.5 millimeter, and the correlation was relatively high here. And then we look at resting state in the beta band. So here it was beta power. So you see nicely the power in the central sulcus during beta activity. This is the power recorded in MEG. Of course, the central region was not covered, but this is what we could get. And this is what we get from the MEG. And here we have a correlation of 0.5, which was quite good. And then we did connectivity. And for instance, here I'm going to show you connectivity with a specific seed point here. So if I choose a seed point here, this is the connectivity using amplitude envelope correlation in the beta band. And this is what you reconstruct from MEG. So here we get a correlation of 0.5, but as you can see, the correlation, especially the connectivity for MEG was very high for the envelope correlation because this metric is sensitive to leakage. So if you orthogonalize, you remove the effect of leakage, you get similar value now around 0.2 and the correlation, which is quite good. And if I summarize, and this is my last slide, if I summarize the result, for distance to spike over our 9 subject, we found some distance ranging from 1 or 2 millimeter to 2 or 3 centimeter and of course, as expected, the deepest generator were the most difficult to localize. When localizing resting state oscillatory patterns, we were quite good. So the spatial correlation was relatively good, especially in the alpha and beta bands. And when we were comparing functional connectivity directly in SEEG or from MEG converted to SEEG, it was quite good for those two metrics that are sensitive to the leakage. But when you remove the leakage, the effect of zero lag leakage, then you reduce the value, but amplitude envelope correlation still showing good value. But when doing connectivity during pure resting state as WPLI, it was probably not an appropriate metric to study that. WPLI is probably more appropriate when you study connectivity at the time of ictal activity, at the time of spike, at the time of a specific cognitive task. So to conclude, MEG source imaging from superficial region is accurate. Interpreting deep brain activity should still be done with caution. We are progressing, but there are still some mistakes. Amplitude envelope correlation overestimates MEG connectivity because source leakage, and orthogonalized version address this. So we recover better the connectivity patterns, but we can also remove true zero-lag connections. Our findings at the single subject level done in this study in preparation using MEG and SEEG at the same time is concordant with the study I showed you before at the group level compared with the intracranial EEG atlas. So we believe that those tools, and especially how you estimate SEEG data from MEG, can be quite useful when planning SEEG implantations. All those tools are implemented inside Brainstorm and with our plugin, which is called Brain Entropy in Space Center. So you can find it. And I'd like to thank, of course, all my lab, the key people who did that work, Shifa Abdallah, Jawataf, Nan, Tamira, Victor, to quote a few, or Giovanni Pellegrino, my main collaborator, Birgit Frauscher, Jean Gottman, also Christian Bénard and Jean-Marc. Thank you very much. And I'm ready to take questions.
Okay, thank you, Dr. Grova. It's very informative. A lot of data that must have taken years and years to sort through. That's a very impressive data set that you've worked through there. We do have a couple of questions. Let's see here. We have some coming in now. First question, very interesting talk, comparing different modalities to the gold standard stereo EEG. How do you see this being used in clinical practice? And do you think it could reduce the need for SEEG?
This is the main question. I'm not sure. It could perhaps in some case, but what I am convinced is that, especially because we can mimic, and that's what we are working on right now, you can predict how from a MEG data or from EEG, it's the same, how the SEEG signal would look like according to your source imaging. You could then optimize a bit more quantitatively the implantation. So it doesn't mean we avoid completely the clinical decision. It's not a pure automatic implantation. Like SEEG implantation requires a huge knowledge and you have targets. But when we know what is the target we want to reach, probably this technique might tell us, okay, do perhaps a bit more data orientation, and you're going to cover a bit more accurately the extent of the underlying generator. So that's exactly. So replacing SEEG, I don't think so, but improving the chance of succeeding in SEEG and being and improving objectively the implantations, I think yes.
So on that, I kind of have a question also. What do you think, given the current lay of the land in these, level 4 centers, what do you think are the most critical modalities? I mean, so here we talked about, like, if we apply your techniques, what are the most critical modalities to use to be able to answer these important clinical questions?
Of course, like as usual, like so I'm an engineer. I'm not the neurologist. I'm assisting them. I'm helping them. So I do believe that the reading the EEG remains the most important. checking accurately the anatomy and the underlying lesion with MRI and nuclear medicine. I'm just saying that EEG or MEG provide really quantitative results when we turn to source imaging. With some, I did not go into those details, but if you have the chance to have access to a MEG or to more high density EEG, it's probably better and more accurate. But we are showing more and more that if you have a lot of trial, like long recording with low density EEG, you could still do some decent job, not perhaps as accurate, but it's quite informative, and we have some projects going on that at that level as well. So that to be broadly used, largely used by many epilepsy centers, even if you don't have access to a MEG, for instance.
Got it. Thank you. We have another question here. I'm curious if there's an application to phase reversal / central sulcus mapping with the MEF here, since that is rather surface based. Logically, would it change the workflow?
Can you repeat? I'm not sure. Are you talking about task or the task, like a face recognition task, or no, phase reversal of the signal in the? I'm not sure I understood the question exactly.
Yeah, I think it's the phase reversal of the signal, the central sulcus mapping with maybe that's maybe that's MEG.
Yeah.
So yeah, let me reread this. Sorry, there. Curious, there's an application to phase reversal, the central sulcus mapping with MEG here, since that's rather surface based or superficial. Logically, would it change the workflow?
Yeah, I'm still not sure I understand the question. I'm relatively more convinced that the more we can put into the problem is ill-posed, as we all know. And of course, you put a single dipole, you can have any orientation, and as it was shown largely by Dr. Bersol and others, then the orientation of that dipole is quite informative per se. I do believe that source reconstruction along a cortical surface by fitting the orientations or keeping it a bit loose is also quite informative, because we believe strongly on the anatomical support where those data are generated. And I would be more in favor of things like that than having more of a 3D grid where dipoles are allowed in any direction. I know it's a question of choice. Probably there are pros and cons in doing that. That's mainly what we have been doing, and we show that this is serious information that has been taken into account, and you can use also model comparison to show that when the anatomy of the subject is taken into account, there is information that the model is using. So I think it is important. It's a bit more tricky, which is another question when we go to deeper regions, because then the model of fixed orientation is not so true when we want to perhaps target challenging regions like the thalamus, which is what we're going to try in the future. But so I'm not sure I answered the questions, but if it's volume versus surface-based mapping, that's the way I see the problem.
Thank you. Next question. Excellent talk. Do you believe that any other modalities could be used to quantitatively or qualitatively infer joint probabilities of the epileptogenic regions better for targeting with stereo EEG?
Yeah, definitely. We can have interesting models that are being combined to create mapping. There are a great project like the Virtual Brain Project using mainly EEG and tractography, diffusion MRI, that has been proposed by notably the Marseille group from Victor Girsat to make that kind of probability. I believe EEG MEG source imaging has its role in doing that together with other modality. That's probably something that can be known, and we have nice tool using Bayesian framework now, where we can really try to see what's going to be the influence of that or that modality a bit more quantitatively than just as an observation aspect as most of us were doing in the past.
Thank you. Let's see, next one here. Do you think that most of the neuroelectrical activity in the subcortical structure can be effectively recorded at the scalp? Is this the main reason that MEG faces the same challenge as other methods when dealing with sourcing the deeper structures?
This is like I can do another talk more specifically on that, but that's a big challenge. And we showed recently in another paper we published in Human Brain Mapping, we put a depth-weighted aspect to our MEM. So we show we are a bit more sensitive to depth. We included a specific surface of the hippocampus in the model, and that did improve. But still, and that's what we see also in the simultaneous recording, we have our signal are sensitive to deep activity. And people who have been using simultaneous recording have shown that if you average based on the SEEG a deep generator, you're going to see its trace on the surface. But when you start from the surface, it's getting really challenging to see it. So I believe there are ways we can address it. We need more efficient signal processing, perhaps AI or other aspects to be able to see, to extract it, because it's clearly embedded in the noise. And one main issue, for instance, we showed that we could localize relatively deep regions when we look at the very initial rising phase of the spike. But often, even if we do that, at the same time, we always get like confounding or spurious localization more on the surface. And so to disentangle those two, it's still not so clear. I hope that our simultaneous recording will help us to develop methods that could tackle this problem. So I would still be quite cautious. We don't see deep activity. I think it's there, but being confident in our localization of deep activity, I don't think we are there yet.
Got it. Thank you. All right, so I'm kind of curious about your myself, the oscillatory findings that you have and connectivity, and you spoke a bit about phase, and it sounded like phase wasn't very helpful in these predictions. So I'm wondering if you have incorporated, or do you know of other groups that have incorporated DTI data into their connectivity, like using it maybe as like a way to weight the coherence comparisons?
Yeah, there have been some work that tried to at least correlate or to map, to guide the mapping using tractography. Tractography has its limitation as well. Like there are some connections that might exist, especially when it's connecting one hemisphere to the other, that are not always well detected in diffusion MRI. So we haven't done that for the moment. And just to give a note, what we found is that the envelope correlation was, especially orthogonalized, was a very nice metric when we compare during pure resting state. And it doesn't mean that phase are useless. And when you look at the literature, metrics that are using phase have been quite successful when you deal with ictal data, when you deal with oscillations, gamma oscillations during cognitive tasks. But during pure resting state, I think the phase is more local and it's not such an accurate metric than the amplitude. But the two I'm measuring two different mechanisms, and that's also the reason why it's getting a bit confusing, because we have different method plus different metrics. So we need to see where are our hypotheses in this framework.
And your beam forming, what signal was that based around? Like, was there a reference signal? What were the data that were fed into the beam former? Is this ictal activity that you're using?
No, it's there was one slide when I was comparing MEM, minimum norm, and beamformer, for instance. In those techniques, like it was just pure resting state. It was 60 seconds of pure resting state data. So we selected a clean 60-second segment with no spike, no ictal activity, just eyes closed resting state. That's it. So that's why this resting state has some properties, has some ongoing properties that might already differ in the epileptic brain compared to the healthy brain, and it has been suggested. But for that, we believe the envelope correlations were a little bit more robust. And there have been other studies that shows that they were also looking at more like the fMRI resting state fluctuation. The phase metric were not robust in that case, whether it was beamformer or, but in all cases, it's the source reconstruction technique, MNE, beamformer, or MEM were applied to the same 60-second resting state data.
Understood. Thank you. Dr. Grova, thank you very much for the wonderful talk. It's an extraordinarily data-rich talk. I really enjoyed that. So thank you very much. Thank you to the audience for attending our NeuroTalks. Please keep an eye out for our upcoming newsletter and talks that we have. We really appreciate everyone's attendance. And again, Dr. Grova, thank you very much for the wonderful talk. We appreciate it.
So William, before we dismiss the group, let me and thanks, Dr. Grova. That's a wonderful talk and a very informative and such great developments in this domain. So our next talk for our NeuroTalk community here, we will have our next October NeuroTalks going to be in October 17th. From 11 a.m. to 12 p.m. Eastern Time. And it's a featured speaker, Dr. Marcel here from the University Hospital Freiburg. So, and his topic is going to be advanced multimodal imaging in pre-surgical epilepsy diagnostics, electrical magnetic source imaging, and MRI morphometry. So looking forward to that, and watch your email and register, and it's going to be another very wonderful talk. So again, thank you, Dr. Grova, for share your wisdom here, and thanks. And
one more, sorry, I'd like to add one more thing before we finish up. We also have our upcoming epilepsy workshop.
Oh yeah.
October 13th, week of October 13th, Wei, if you want to.
Yeah, October 13th, it's going to be a 1-week workshop. Every session, it's going to be 3 hours from Monday to Friday. And we actually going to send invitations. Watch your email. This will be led by Dr. John Alboso to teach us how to use the curry for the pre-surgical phase 1, phase 2 planning. So yeah, if you are interested, please register. Thank you.
Thank you for having me. Thanks a lot.
Thanks, Dr. Grova. Bye-bye.
Bye-bye.